Hello learners, you are listening to our learning series. In the previous session, we have gone through the basics of quality for a manufacturing industry. In this session, we are into the basics of GD&T. This session will be helpful for beginners before reading the engineering drawing. Let's begin today's session. GD&T. The abbreviation is Geometric Dimensioning and Tolerancing. As in the name, it is a combination of geometric symbols, dimensions and tolerance. It is the universal language in a manufacturing and engineering. It is used in aerospace, automotive, robotics and precision manufacturing. It reduces manufacturing errors and rework costs also. This is essential for quality control and inspection. It ensures parts were fit together correctly and functioned as planned. Why it is important for a manufacturing? Because even if a small mistake in engineering can cause product failure, it even creates a safety issue also. So we have to give more importance to this. Now let's see the important terms in GD&T. First is feature, next is tolerance and the third is datum. What is feature? Any geometric shape on a part is called as feature. For example, a hole in a bracket, a flat surface on a block, a slot for a bolt and a cylindrical shaft. Any shapes is a feature. Next is tolerance. It's nothing but allowed variation or acceptable variation. The variation may be in size or geometry which is defined for a particular dimension. It will be always based on the fit or function. Next, what is datum? It is a reference point, line or surface used as a base for measurement. Means what? Everything is measured from the datum. In a simple word, it is your measurement reference. Feature control frame. What is feature control frame? A box on a drawing that specifies exactly what geometric requirement is needed. This is what a feature control frame looks like. First is GD&T symbol. This shows which geometric requirement it is, position and diameter. It may also be a straightness, flatness, position, etc. Next is tolerance. This is the numerical limit for a diameter, that is 0.2 mm. So how much variation is allowed here? 0.2 mm. This 0.2 mm is called as tolerance. Next is datum. It is the reference surface or points. Not all the control frames use datums. Here the datum is A, B and C. Its primary, secondary and tertiary references in order of importance. Now we'll see the basic GD&T symbols. Here the symbols were grouped by what they control, like form control, profile control, orientation controls, location controls, runout controls. Let's see one by one. Form control means how a single feature shapes itself. Here the form controls are straightness, flatness, circularity and cylindricity. All these four features don't take the references. It is a independent checks. Next we'll see profile control. It projects the complex shapes, profile of the line and profile of the surface. Profile of the line gives the accuracy of the irregular shape. Profile of the surface gives the accuracy of an irregular surface. Here if you see, only the shape and surface is a difference. It is used for the curves, irregular shapes and complex geometry. Next is orientation control. Here the feature relates to a reference always. Parallelism, perpendicularity and angularity. Parallelism stays parallel to the datum surface or axis. Perpendicularity takes the reference of 90 degree to a datum. Angularity is a specific angle with reference to the datum. You have noted all these three are taking reference of the datum, that is orientation control symbols. Next is location control. It tells where a feature control is positioned. Position, concentricity and symmetry are location controls. Position tells where exactly is the hole. Most important in GD&T. Concentricity. It tells how centered is one circle within another circle. Symmetricity. It tells how centered is one feature relative to a center line. These location control symbols were used for assemblies where precise location which determines fit and function. Next is runout control. Runout controls gives the rotation accuracy, circular runout and total runout. Circular runout tells how much wobble is there when rotating. Total runout gives the total variation across the entire rotation. It is used for rotating parts like shafts, wheels and cylindrical parts. Now let's understand tolerance types. There are two types of tolerances. One is unilateral and bilateral tolerance. Why there are two types of tolerances? Manufacturing must balance precision with practicality. Different situation requires different tolerance approaches. Let's see in detail. Unilateral tolerance. Here you can see a shaft and a hole. The shaft has to be inserted into that hole. Here the hole diameter is 10 mm. So the shaft diameter should not be more than 10 mm. So it must be 10 mm minus 0.05. Nominal value is 10 mm. Acceptable range is 9.95 to 10 mm. This ensures the part will always fit into the mating hole. Now bilateral tolerance. Here the nominal dimension is 30 mm is having the bilateral tolerance of, that is plus or minus 0.1 mm. Nominal value is 30 mm. Acceptable range is 29.9 to 30.1 mm. These tolerances are normally used for non-critical features. To choose the correct tolerance type, we must know the difference between accuracy and precision. If a part need accuracy, tighter the positional tolerance. If a part need precision, tighter the feature controls like flatness, circularity, etc. Knowing the difference helps the designers to decide which GD&T control is required. It also helps quality inspectors to have a good control over the part and decides whether the process is consistent or not. So let's see the difference. In simple word, accuracy is closeness to true value, precision is repeatability or consistency. In this picture, center point of the circle is the nominal or true value. The other points are the measurements of the different parts. The first circle shows all measurements are close to the true value as well as close to each other. So it is both accurate and precise. The second circle shows all measurements are almost close to the true value but not close to each other. So it is accurate but not precise. The third circle shows no measurements are close to true value but all are close to each other. So it is not accurate but precise. The fourth circle shows no measurements are close to the true value, also not close to each other. So it is not accurate and not precise. From the feature control frame, as of now we have seen the symbols and tolerance, right? Now we are going to see the datum. Datum provides a consistent reference for the measurement. It allows the manufacturers to consistently build the part. Also, it allows the quality inspectors to consistently verify the part. So, it ensures parts fits together in assemblies. The reference may be point or line or axis or plane. Here, datum A is a flat plane. So, you have to place the part firmly against this surface in the inspection setup. Then, you have to align the cylinder with a measuring spindle and rotate the part. During the rotation, any wobbling, out of round, tilt or bending is measured relative to what? This datum A. And the allowable deviation is 0.03 as per this drawing. Now let's see the important GD&T symbols one by one. First is flatness. Imagine a tabletop or laptop. It looks flat over eyes, right? But it must have some small bumps and waves. Flatness tolerance controls how much those bumps are allowed. Here in this drawing, it is 0.03 mm bumps or waves allowed. Next is straightness. A shaft should be perfectly straight like a rod, but in reality, it may have some bend slightly. Straightness controls how much bending is allowed. Here in this drawing, it is 0.03 bend is allowed. Next is perpendicularity. Two surfaces that are perpendicular are at 90 degree to each other, right? Like the corner of a room. Perpendicularity tolerance controls how close to 90 degree they must be. Here in this drawing, it is 0.03 mm bend is allowed from 90 degree with respect to the datum A, that is the bottom surface. Next is position. It is nothing but where is the hole, not just its size but its exact location. Position controls how close to the ideal location a hole must be. Here in this drawing, the actual center of the hole can vary but must remains within a cylinder of 0.1 mm around its true location. With respect to what? The datums A, B and C. Next is parallelism. Two surfaces that are parallel stays the same distance apart throughout the length, right? For example, imagine a railway track. Here in this drawing, the top surface must stay parallel with respect to the datum A, that is to the bottom surface within 0.03 mm. Next is runout. When a shaft spins, does it wobble? Yes. Runout controls how much wobbling is allowed as it rotates around a datum axis. The left cylindrical surface must not wobble more than 0.03 mm with respect to the datum A. As of now, we have gone through a very basics of a GD&T, but there is a lot in this chapter to understand, which will be explained in a very simple manner soon in this channel. Please do visit this channel for continuous learning. Thank you.